Okay, hello everyone. Today we will learn properties of point estimation, which is chapter 9. In this chapter 9, we will going to learn some mathematical properties of point estimators related to efficiency, consistency, sufficiency, Rao-Blackwell theorem, and etc. We will start from relative efficiency. Chapter 9.2 is about relative efficiency. For unbiased estimator, we prefer to use the one with smaller variance. So that's where the relative efficiency comes from. Definition 9.1, given two unbiased estimators of zeta 1 hat and zeta 2 hat of a parameter zeta. If the estimators are unbiased, then we prefer smaller variance. So the relative efficiency is just comparing the variance of each estimators. So each estimators have variance of zeta 1 hat and variance of zeta 2 hat respectively. Then the efficiency of zeta 1 hat relative to zeta 2 hat denoted by this term EFF zeta 1 hat comma zeta 2 hat, and it is defined to be the ratio of the variance of those two. Okay, so let's move on to example 9.1. Let y1, y2, and yn denote a random sample from the uniform distribution on the interval 0 theta. Two unbiased estimators for theta are these. And the problem is find the efficiency of zeta 1 hat relative to zeta 2 hat. So we want to find the efficiency, relative efficiency of zeta 1 hat relative to zeta 2 hat. And this is the variance of zeta 2 hat over variance of zeta 1 hat. So we just need to calculate the variance of each estimator and plug them in the formula. Okay, and the distribution function for y is fy. It follows uniform distribution, so it is 1 over theta from the interval from 0 to theta and 0 otherwise. And from uniform distribution, expected value of y is theta over 2, and variance of y is theta square over 12, and you can derive them directly, but we already derived this from previously in the mathematical statistics 1 course. So we will admit this and proceed. And the first thing is to calculate the variance of zeta 1 hat. So variance of zeta 1 hat, which is variance of 2y bar, and this is variance of 4 times variance of n over y1 plus dot 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 yn, and this term n is constant, so this is n square, and since y1 to yn are independent, we have n number of variants of y's, so this is 4 over n variance of y, and variance of y is theta square over 12, so this becomes theta square over 3n. Okay, and also we can check that our estimator zeta 1 hat is unbiased estimator by calculating expected value of 2 y bar, which is 2 times expected value of y bar, which is 2 times zeta over 2, and this is zeta. So we calculated, so far we calculated variance of zeta 1 hat. So next thing is to find the variance of zeta 2 hat. Variance of zeta 2 hat. And zeta 2 hat is n plus 1 over n yn. So this is n plus 1 square over n square variance of yn. So we need to derive the variance of the maximum of yi's, and we know how to derive the density function for maximum value, which is from the formula g y n y. From the formula, this is n times f y y n minus 1th times f y y. And from the distribution of y is uniform distribution. So fy is probability of y is less than or equal to y, and this is y over zeta or uniform for this distribution. So y over zeta and n minus 1th and 1 over zeta for the interval y is greater than or equal to 0 and less than or equal to zeta, and we have 0 otherwise. So from here we can calculate the variance of yn. Variance of yn is actually equal to expected value of yn square minus expected value of yn square. So we want to calculate expected value of yn, and this is integrating this is n over zeta nth and y n minus 1 times y times dy from 0 to zeta. So this is n over zeta n and yn. So n plus 1 y n plus 1, and from 0 to zeta. So this becomes n plus 1 over n times zeta. Okay, and from this part you can know that the expected value of n over n plus 1 y n is zeta, and so this one, which is zeta 2 hat, is unbiased estimator. You can also check that, and we want to calculate expected value of yn square, and this is from 0 to zeta n over zeta n y n minus 1 and y square dy, and this is n over zeta nth, and we have y n plus 1, so this time n plus 2 y n plus 2 from 0 to zeta, and this is we put zeta here and zeta square n over n plus 2. Okay, so what is the variance term? The variance of this thing, let's mark this thing is n over n plus 2 zeta square minus n over n plus 1 square zeta square. Okay, and next thing is put this star to here. So this 2 star is n let me use blue color, n square n plus 1 square, and the variance of yn is this thing, so n over n plus 2 minus n over n plus 1 square zeta square. And from here, if you multiply it to the first one, it's n plus 2 and n times n plus 1. Oh, no. N plus 1 square. And minus 1 zeta square. And this is the upper term is n squared plus 2n plus 1, and this term becomes n plus 2 n squared plus 2n. If you minus this one goes out, so this one becomes 1 over n plus 2 zeta square. Okay, now we calculated all the variances. The variance for the zeta 2 hat is this thing. So the relative efficiency of zeta 1 hat related to zeta 2 hat, which is variance of zeta 2 hat divided by variance of zeta 1 hat, and this is the variance of zeta 2 hat is from the previous slide, zeta square over n plus 2, and the variance for zeta 1 hat is zeta square over 3n. So this one becomes n cancelled, and we have zeta square cancelled, and we have n plus 2 here and 3 here. So our answer is 3 over n plus 2. And as you know, the relative efficiency is getting lower and lower as n is increasing. So what this means is that the efficiency for zeta 2 hat is better than zeta 1 hat. So our relative efficiency is here, and as you can see, as n goes large, the relative efficiency always going down. So zeta 2 hat is more efficient than zeta 1 hat. Okay, this is end of the class for this week. Thank you very much. In next week, we will go over one more exercise problem for the relative efficiency, and we will move on to next concept. Okay, thank you.